Hello, everybody. How are you? And thank you for joining us today in this webinar about ceramics 3D printing for aerospace applications. Um, we will wait a couple more minutes for more attendees to join. And my colleague here, Ruslan, will start the presentation. I appreciate your patience and thank you for joining us. And thank you very much for being here today. Let me quickly introduce you. Ruslan is one of our colleagues from 3DCERAM, one of our partners and the partner we trust when it comes to work with ceramics 3D printing. And please, can you give us a quick introduction about 3DCERAM and start with your presentation? And thank you.
Yeah, thank you very much, Harry. So thank you for inviting for this webinar and giving this possibility to share some experience and information about the additive manufacturing and for the new space applications. So before starting speaking really about these applications, just short introduction of about our company. 3DCERAM's Sinto started about 20 years ago. It was 3DCERAM first, and we start from printing the parts, ceramic parts. It was first 3D printed parts for different applications. Actually, we started from medical applications. And over the years, we came to change our business model. And today, first, we belong to big Japanese group, Sinto, which is our main shareholder since a couple of years. Sinto has more than 70, almost 100 years of experience mainly in foundry equipment. And their vision is to develop these applications, and ceramics are something they see big potential for. So today, 3DCERAM Sinto has a worldwide presence. We have subsidiaries in US and China, and distributor maintenance qualified in these countries, also in Armenia. And company itself is located in Limoges. It's about 350 kilometers south of Paris. About 30 people, where we manufacture our printers, slurries, develop our software. So as I said, 3DCERAM Sinto is the process provider. So we propose and manufacture our range of 3D printers. We develop our own software to facilitate the preparation of the build plates for these printers. We prepare our own mix that we propose to our customers. And of course, we render some dedicated services going from the maintenance training to the support, customer support during the manufacturing, during the production stage. Now about space in general, additive manufacturing space, of course, you've heard about some applications in metals 3D printing, polymers, resins 3D printing. What about ceramics 3D printing? When we speak about the ceramics, of course, you can imagine some brittle parts, which are maybe not very resistant, and we have to deal with many constraints during the launch stage and even during the in-orbit flight. So I will not. You can read these constraints on the slide, but there are many, from mechanical, thermal, and electronic or electromagnetic constraints. They are existing. So all the parts we print from ceramics should fit to the requirements of the operation in space. What are speaking about the space, we have conventional space industry, so big national space agencies, big satellites, solutions tailored for each particular projects. So it means that the technical level is very, very high, and these conventional space applications are really run by big companies or governmental agencies. The main constraint, in addition, on the top of all these constraints already listed for the conventional space, the maintenance is not possible. So when we deal with some one-shot launch, some very particular tailored solutions, additive manufacturing can be useful for two aspects mainly: choice of the right material, ceramic material, the trade-off with metals already used in space, and work development of exploration of new shapes. We have this experience that we collaborated with company Thales Aerospace, TAS, where silicon nitride slurry was developed and adapted for the 3D printing, and mainly for the space applications. So this material was developed with the powder, with the customer powder, with TAS powder, and we adapted this powder for to make a slurry to be printed with our SLA technology. And all our battery of tests showed that the properties of this material was good. I mean, the same, similar to the parts manufactured by traditional method. You can see here the mechanical strengths. We could get about 800 MPa. The goal was about 670 MPa. So we even over, we could better than the target. So this was about the material qualification. The shape qualification, you had to design or redesign the parts which would be easier, I mean, lighter, more functionalities for the space industry. So the parts, I mean, here you have the example of the part which was already in ceramic, but we could also work on some parts which were in aluminum or in titanium, and we could do them in different type of ceramics. By additive manufacturing brought some new functions, new features to these parts. We could make them lighter and more rigid for the applications required for this application. Now about the new space. New space, we distinguish new space from conventional space by all these mini and nano satellites, constellation of satellites, low Earth orbit. The maintenance is not still possible for this for these devices. But if you lose one satellite, you don't lose all the function. I mean, you lose millions of investment because the task can be dispatched to other satellites of the constellations. Applications for this are many, from telecommunication to radar or navigation systems. And here the benefits of additive manufacturing is that we can do ceramic parts compact, lightweight, with high performance and high quality. And especially what is very appreciated is the affordable price, because these new space companies, they want to do the satellites like the cars or the conveyor. Here the approach is different because we adopt a kind of mass customization for these parts. We do not speak big satellites. We do not speak every particular project. We speak some solutions which can be standard or can be adapted to each particular solution, but in I mean for the similar devices. Of course, the development time should be shorter, and the lead time from the prototype to the production should be also shorter. Just sorry, I have some noise. Sorry, stop. Sorry for this. So additive manufacturing brings more flexibility, allows to reduce this development and lead time. And we are speaking sustainability as well, because we use the solutions which are really tailored for each particular part. But this part, you don't need to speak big series of products. We have no tooling. The tooling is digital. Just remind what is additive manufacturing. So of course, this solution can be used, adapted, customized to every small satellites they do. And we are dealing with the small companies. It's not governmental agencies, it's just commercial space companies, which can be very small, like what we did already in France. I will show you the example a little bit later, or mid-sized companies. Every project starts from the prototyping. And here we come to the solutions we can propose for this application. For prototyping, we have two types of solution. The first one is our matte machine. It's a kind of desktop printer, rather versatile unit, which can be equipped with different extrusion additive manufacturing tools. These tools are FFF, pellets, rubber casting, one or dual components rubber casting, and it's very interesting and very advantageous for some people who's working already with FFF, that this machine can be also equipped with green CNC machining, 3-axis machining tool, which can be also hosted by this frame. So we speak about some universal, small, affordable in terms of the budget machine, which can do different prototyping parts. I insist it's not for the production, it's not for the industrial production, it's just for the prototyping, for education as well, for development. But the industrial application needs bigger printer, more industrial printer. We'll speak about it a little bit later. So here how it works for the FFF. So this machine is designed to work with different kinds of ceramics, including silicon carbide, which is not possible with another technology I will speak about. So we can go rather quick to get very, very nice quality of parts. And you see here, it's an investment core. It's just ceramic core for the investment casting, which is printed on this machine. It goes really quickly in very short time. You can get your part. You can you still have the debinding and sintering process, which is necessary for ceramics. Additive manufacturing of ceramics, it's the printing is just the shaping of the parts, but you can go much faster in terms of the printing. And as I said before, the printing can be combined with the machining. So you can see here how it works. So you print some layers, let's say 5 layers of the parts, and you can machine them in green stage to start reprinting again and again. So your part can be enhanced in terms of the roughness of the surface, but also in terms of the density of the part, because FFF printing convenient is that where you turn this filament, you create some porosity, and the overall porosity density of the part is not ideal. So doing this green machining on the surface of the part, we reduce or we densify, we reduce these pores, and we densify in this way the part. Just a note here, you can see the debris on the build plate. So this is just for the demo. Of course, we have the vacuum cleaning station, which is removing all these debris during the operation of the CNC. Filaments can be proposed, I mean, standard filaments which can be proposed are alumina, zirconia, silicon carbide, but also we can print with metals on the same machine. We can print titanium, space grade, we can print stainless steel, we can print copper, and also it's just the standard material we propose. But as this slide shows, a new filament, completely new filament, this is the example of regolith one, can be developed rather short time. The thermoplastic method is known, so we can develop it, let's say, in 1.5 to 2 months from some given powder from the customer, for example. In the past, we could develop some electroconductive ceramics. We could develop ferrites. We could develop corduroy. All this with the filament for the FFF technology. When we speak about the prototyping to industrial production, in this case, we speak more about SLA, stereolithography. This technology is used either for prototyping, but also for small size or small series or average size production, but also for the production of the very big parts. How it works? SLA is stereolithography. When we cure with a laser, UV laser installed above the printing platform, we cure the slurry, which is the mix of ceramic powder and photosensitive binder. So typically, you dispatch your layers of ceramic slurry, and you cure each layer in each particular location. You cure with this UV laser. For sure, you know already some SLA technology in resins, maybe in metals, so it works in the same way. There are a lot of advantages of this technology comparing to other polymerization technologies like DLP, but it's not the subject of this meeting. But if you have some questions or what are advantages of SLA versus DLP, we can answer after this webinar. When we work with all these commercial space companies, what is their approach? It's very important to understand how we work, because these machines, this technology is not just plug and play technology and when you can do anything from ceramics. No. We have some dedicated approach, which consists in several steps, let's say in 3 steps. First, we do the risk analysis. You provide us your CAD file, review the feasibility from our point of view, from printability point of view, from cleaning point of view, from thermal process point of view. Then we give our conclusion and we try to collaborate with you to co-engineer the part to remove totally the risks of 3D manufacturing. It means that not every part can be adapted for the printing. Depends on the materials, depends on the size of the printer, but also depends on the shape of the part, or the section of the part, section thickness, for example. I said that we use the slurry. Slurry is composed from the mix of, from the ceramic powder and photosensitive binder. So we use for SLA technology rather high-loaded slurries where we have more than 55% in volume of ceramic powder. It means that we reduce the shrinkage, but we still have the shrinkage, which is something common to any shaping method of ceramics. So this shrinkage makes us some challenges that we have to deal with. And the design to manufacturing step is just about these challenges. We try to see what is the best way to print this part vertically, horizontally, maybe in some different way, with the supports, without the supports. By the way, this technology, because the gravity is working for us, gives us the possibility to use much less supports than what is used for DLP printing, for example. So this is design to manufacturing step, which is about to understand, to learn how we print the part. And then the third step is production, is decision of the customer. What is the best way for him to go forward? Either to outsource this to one of our partners, because we do not manufacture parts for the customers, or maybe to install the machine in-house, because you have some particular projects, you want to keep confidentiality of these projects, you want to develop your own know-how. You don't have many of these parts usually in space industry. Even for the new space, we are speaking maybe thousands or tens of thousands of parts, but not millions of parts. So it makes sense. It can be calculated. We can help you to calculate this from technical and economic point of view. We can do provide you some inputs to calculate the economic feasibility of this project and to see what's the best solution for you. So from prototyping, when we go to the industrial way, either we use for the prototyping, but quick prototyping, MAT, or we use our SLA range of printers to go to prototyping and then to the production. Very important to understand here that prototyping with MAT doesn't give you the possibility to use the SLA printers. We do not speak the same technology, so whatever you do with the filament, you cannot really say that it will be the same with SLA. No. MAT machine is just cheap, affordable machine to go fast for some tests, try to develop some new shapes, new parts, maybe test some materials, because the properties of the ceramic materials, ceramic sinterate materials, are more or less similar. But you cannot say that from MAT you can just copy paste on the industrial solution on SLA printers. This is possible with SLA printers manufacturing and prototyping and scanning out. We have 3 size of printers, from the smallest one, which is 100 by 100 by 150 in Z, to the biggest one, which is 600 by 600 by 300. All of them use the same type of lasers, the same slurry, roughly the same slurry, same interface. So you can easily go from the small machine when you do some R&D works to this large series machine, C1000 Flexmatic machine, the build weight plate of which is 300 by 200, or even to the biggest one, which is 600 by 600 by 300. Study cases. The purpose of this webinar was not only to review different technology we can propose, but also to review our experience, to share our experience. So we have some couple of study case we can share here, because some of them are under NDA, so we don't really can talk about it. But first one is S-band antennas in zirconia printed for company Anywaves, which are allowed to increase the permittivity of the antenna, to increase the quality, and also to print in very flexible way different lattice structure of this small parts, small patch called antenna. So why they did choose the additive manufacturing, and why zirconia? Zirconia, it was something that this material is known for the antenna application because of its high permittivity, and we can print with two types of zirconia, which is available in our standard portfolio. It's zirconia stabilized 3% yttria and zirconia stabilized 8% yttria, which is used for electronic applications. So this latter one was used for this antenna. And additive manufacturing was adopted because, first, it could ensure short lead time to raise the maturity of the part, to test it, and to make it fly, and tuning capability, because we can easily adapt. Again, we don't need any tuning. The tuning is just digital. So we can do, let's say, 2 or 3 different shapes of the same antenna in one print. And we can do it in a very flexible way. So if the antenna you printed doesn't work well, has to be enhanced, you don't need to change a tool. Just change the file and you reprint it again. So it's a matter of days, not months. And it was 100% European technology, which was very important for this company. So here how it looks like. So this is already assembled antenna. You can see this white lattice structure which was printed. So of course you already know that lattice structure cannot be, even for other materials, cannot be easily done with other methods. So here lattice structure and printing are compatible. And also we could really make it in 18 months, we could raise the maturity to the point when the customer decided to buy a printer and to print these parts itself. I think I'm not wrong, is I think the first satellite with these antennas was launched in October or November 2022. So it's already used in space. And these antennas are already proposed by company Anywave, and they take also on American market as well. Another study case we can share is about some, I cannot show the part, it was part in alumina, so different material, which was used for in iodic thrusters for the company Trust Me. Also a small company, a small startup, about 30 people in France. And here it was not about the shape, it was for an economic reason. First, when they tested the alumina part, they could get good results in terms of the lifetime, and they also could integrate new features to this part. The part is not very complex. It's print because they don't need very big series of this part, and they also adapt this part to every different function. So it can be different size, different diameter. It's kind of cylindrical part. And they do not need to make all these many tools to customize the thrusters to different satellites. So the same like for the previous case, November 2020, we did the first one of the first prototypes. We could study with them and could co-engineer with them. And 1 year later, they could start serial production. Let's say serial, it's not really, it's serial, it's mass customization we see, because as I said, in one run, you can print different parts of the same typology from the same material, of course. Cooperation and co-engineering are very important in this case. of course, and this is the main, let's say, model of this presentation, that we do not know your application, your particular application. We do not know your particular working operation conditions. We know our materials, we know how to print, we know how to clean, we know how to post-process the part after the printing. So if we put this experience together, if we put these skills together, we can get good part at the end of the day. But it means that we have to co-engineer, to collaborate, and sometimes it's difficult. I understand that some information cannot be shared from the industrial company to 3D printing process provider, but even in this case, we can go forward by using some the skills we already have, some typologies, some let's say, some parts which are close to the final design to start to test the part for the working conditions, and also to learn how to print this part. So trust me, the same 18 months from the idea to the prototyping to the 2 months after for the serial production. And you can see the advantage for this particular case. These ceramic parts could ensure for this company. When we speak about the machines, about the printers, all of these works were implemented on C100 or C101 machine. We have two of them different, C101 Easy Lab and C101 Easy Fab. The difference is just about the fitting of the slurry. In the first case, for the lab machine, you can see on the left corner of this slide, red cartridge. When you put your slurry, it means that you can work with rather low quantity of the slurry. Imagine you develop your own slurry. It is possible. All of our machines are open parameters, so you can create your own recipes. It's very important for R&D works. It's not open source. We do not have access to our data, to our fixed presets, but you can develop your own. And we have the possibility since, let's say, 6 months, to provide you the facility to develop your presets based on our own presets. This version is not free of charge, but for people who is interested, we can do a particular, very detailed presentation of this software plugin. So speaking about C101, as I said, the build plate is 100 by 100 by 150. We use the UV laser of 405 nanometers wavelength. Always top-down laser. This is our developed and adopted technology. Machine is very easy-friendly, user-friendly, sorry. That's why we call it easy. And it is particularly interesting for the R&D works, for the education, to develop something, to prototype something, or to make big, small parts, or even to make small series of the parts. We have several customers, including US, who print, who do their production on this machine, because they have small parts, they don't need millions of that, and this machine is fully enough for them. The next machine is slightly bigger, just 9 times bigger. It's 320 by 320 by 200, C1000 Flexmatic machine. So this is used either to increase the output from the small one, when you scale up from the small machine to the real industrial unit. This machine can be equipped with 1 or 2 lasers, still 405 nanometers, same laser we use for C101 machine. And this machine is also equipped with some handling equipment, because you can imagine that big plate means big weight, so you cannot really handle it manually. Very important to say, but this is, this is common to all of our machines. All the slurries can be reused up to 7 times. This is what we say. Some customers use it even more. So typically what you do, the slurry which is just goes by gravity from after the printing to the recovery tank, this slurry is recycled. It means it just filtered, mechanical filter, to avoid any small, any pollution particles, any clumps. And this slurry can be used for the printing. So the process is semi-automatic. This trolley with the vibrating screen and recovery tank is supplied with the machine. And finally, when we speak the big machine can be used for the even bigger output, but particularly for the printing of the big parts, because in space we need also some big parts, typically the supports of different astronavigation systems, astronavigation tools. So we could print the parts of, here you see the example of this circular part with specific cavities, which cannot be done by injection molding. So those were printed. And the diameter of this part is 450 millimeters. Just under you can see another demo structure, kind of honeycomb structure, 550 by 550 millimeters. So the build plate of this machine is big, 600 by 600 by 300, but it's not enough only to print the part. This machine is not easy to use, is not adapted to any application, and the expertise, certain expertise in sintering is necessary, because you can imagine when you do the very big part, you may have some distortion during the sintering process, and you have to pay attention how to sinter this part, which would the best way of sintering. Not many of these machines were installed. We have one in Germany. We have one at company Alumina System. We have another one in China, and the fourth one is installed in company 3DCERAM's in Japan. So why I say this? Because unfortunately we cannot really do the benchmark on this machine. It's very difficult. So either we try to do the benchmark on the smaller one, C1000, or customer have to wait for some lead time, because our machine is not, we don't have free capacity to print the parts. Again, it's not our business model. So what are economic reason to go from the small machine to the big one? It's simple, because of the big plate. Of course, when you take one typical part, kind of spider part, you can see on the plate picture under each machine. You can see that in first case for the prototyping, you can print 4 of these parts in 1 hour 20 minutes on the small machine, 48 of these parts in 6 hours on the mid-sized machine, and 112 parts in 12 hours on the bigger one. So you can see that the time per part is really in relation with the big plate. You can print much faster with a big machine. Materials are very important. We were speaking about the materials for the conventional space, but in general, the materials used for the space applications, we could underline here, highlight some of them. So for airspace, we use a lot zirconia 3 yttria. It's excellent mechanical properties, good chemical inertia, and good dialectical properties. Alumina is used in a lot of cases, not only in airspace, but also in general industry applications. So this material is like, it's also good mechanical properties, high hardness, chemically inert, and also cheap, much cheaper than zirconia. Cordierite is very interesting material we have in our standard portfolio. This material is rigid, has low thermal coefficient of thermal expansion, and it's lightweight. Usually it's used for some optical applications because of its rigidity and low CTE. Of course, other materials are also used when we speak space. We can speak defense as well. And because other materials also can be some non-oxides we have in our portfolio, like aluminum nitride or silicon nitride, some silica-based materials for radams, for example, for those who are familiar with this application. So silicor, it's porous material, it's not dense. It's about 35 to 40% of porosity, but it's high temperature resistant material, and additive manufacturing allows us to bring, to make complex shapes with this material. Zirconia, of course, as I said, we have 2 types of zirconia: 3% yttria zirconia, 8% yttria zirconia, which are used both in defense and airspace applications. As I said, all of our machines are open parameters, so it means that you can develop your own slurries. some exotic slurries. I just share here some examples of materials developed by our different customers. Some of them company creates 3D in Singapore. Some of you maybe know this company because they are selling parts. They're making parts for US market as well. So they could develop some transparent ceramic materials like spinel and YAG. Another company could develop regolith slurry. Matisse lab in France could develop new type of zirconia, which is stabilized with ceria to avoid any low temperature degradation of zirconia, standard zirconia materials we may have for medical applications. So, of course, development time is longer than for FFF printing for the filament. Here you need to work on the material rheology, you need to work on the powder, you need to work on the presets, but this is fully possible. And let's say that 40% of our customers only use our standard slurries. 60% use their own slurries or the slurries they develop or they outsource in other places. So here another example of this translucent or transparent ceramics, which are possible with 3D printing for some complex shape. The application for these structures are limited. Space industry, of course, but also semiconductors. And we are not speaking big parts. We are speaking usually small parts. But additive manufacturing brings here the possibility to make very complex shapes. And this may be interesting in some way, maybe for you. Anyway, just to know that this is possible. So to conclude, 3D printing of advanced technical ceramics allows to ensure the excellent quality of parts. We are speaking the same quality than the parts manufactured by injection molding or pressing, sometimes even better. Short development time is very important. You don't need tooling. You don't need to change tooling in case you develop some parts and the tooling is not okay because the part is not okay. So the delivery time is just about your engineer which modifying new cut file. Flexibility is increased because, as I said, we can print fully different parts at the same time on the same printer from the same slurry. So this mass customization is possible, and this fits with the approach, with the philosophy of new space applications. And cost. The cost is efficient with SLA. Of course, it's not always cheaper to make parts versus injection molding, especially if we speak big series production, but it's efficient in some appropriate case when you do small series or very complex parts, which are just impossible to do with injection molding, or when you speak very particular materials you develop for your own for these printers. And of course, the environment is not, it's last but not least, I mean, the footprint, CO2 footprint, you can relocalize and install this manufacturing facility anywhere, I mean, close to the center to the of the end customer. So you don't need big ceramic facilities to do all these parts, because I know if you saw some injection molding facilities, it requires a lot of equipment, a lot of manual work. So here, just one machine and 2 kilns plus cleaning station. Of course, it's maybe too simple, but just something what all you need. So this is all for me. I will be glad to answer your questions, if any. So you have my contact data on this slide, and thank you very much for attending this webinar again, and hire for it. So I'll let you continue.
Thank you very much, Ruslan. This was very, very interesting talk from you, as all your presentations with you and the technology of 3DCERAM. We really appreciate to have you in our webinars. Thank you very much.
You're welcome.
If anyone has any question, you can just activate your microphone and let us know what is your question. Or if you prefer, you can send us a message in this chat, and we will be able to answer. In the meantime, Ruslan, I would like to ask you about the capabilities on applications where this has to be in contact direct with flame and the capabilities to withstand high temperature applications. For example, more than 500 or more than 700, where usually polymers and metals cannot do it.
Yeah, ceramic materials can go much higher than plastic, polymers, of course. So when we speak about 300 or 500 degrees, any ceramic materials can go, can deal with this range of temperature. But it is very important to understand other particularities or other environment challenges, like the gradient of temperature, the gradient of heating and cooling. It's very important for ceramics, but for all the materials. Chemical environment, media, maybe if you speak about some filters or something like that, what is the media in contact with which this material will be, mechanical load, etc., etc. So we do not pretend to give you the right material just like this, because ceramics is the area where everything is not known yet. It's the maturity of ceramic materials science comparing to others, to metals or to other materials. It's then the maturity is not the same. So we still have some studies, and especially for non-oxides, for example, where a lot of things are not known yet. So what we suggest that to our customers when they ask for some properties or ask for some right material, so we can do some samples, maybe much simpler and smaller to be cheap, and customer can test these samples and confirm or not if this material fits with the requirements they have. So this is unfortunately, this is the only way we can say with 100% of certitude that this is okay or not.
Great. Thank you very much, Ruslan. We have another question from Team Weatherford. The question is, please review materials that can be printed in MAT.
Yeah, MAT we can propose. So MAT has three basic extrusion technologies. First, which is FFF, fused filament fabrication, where we can propose the filament zirconia, alumina, silicon carbide for ceramics. And for metals, we can propose titanium, stainless steel, and copper. So those are standard materials we propose. But as I said, we can develop, we could already develop for some of our customers some particular material. So this takes about 1.5 to 2 months to do, and costs some money, of course, but it's not the same budget, it's not the same development time that for the SLA stories. MAT also hosts robocasting. So robocasting head can be just one or dual component with a mixer inside of the extrusion head. For this head, we do not provide materials because typically these kind of robocasting heads are for inside development of materials. So it's whatever you can extrude will be extruded with robocasting. And for pellets, we can propose right now standard pellets from alumina, silicon carbide, and zirconia. The interest of pellets is the low cost. Some of them are water-soluble binder, not all, some of them. So this is also makes much simpler the debinding process. No need of heat acetone or thermal process, just drying. And for pellets extrusion, you use typically the same pellets that you use for ceramic injection molding. So the cost of these pellets is very, very low.
Great, thank you very much. And please, can you let us know if what about the application of the MAT with metals? What are the metals that you can print with the MAT?
Metals, titanium, we printed these materials. It's very important to say that we do not, just sell the equipment and you try to do something. We ensure that we give the warranty for of the properties for our ceramics because and metals, because all of these materials were qualified either by European Space Agency or by German Institute Fraunhofen. So titanium is it's called space grade. I don't remember the exact brand, but it's used for typically for aviation and space industry. Again, it's prototyping machine, so no real applications, industrial applications. You do some parts to test them and to validate some concept or to validate the design. We were working on filters, on heat exchangers from silicon carbide. On some parts for titanium, it was some support structures, but it was some typical shapes, which are really tricky to do by a different manufacturing method. So it was adapted for the 3D printing, lattice structure or some complex shapes. And it's quick. You print the part from aluminum or from silicon carbide, let's say the part of 20 millimeters of diameter, 10 millimeters of height, you print it in 35 minutes and you have your part.
Thank you very much for your time today, Ruslan, and to all our attendees. We are very happy to host these informative webinars. Also, if you would like to join us in our next webinar on April, you are invited from now. So let's stay in touch, and thank you.
Thank you. Thank you all.
Bye-bye.